We saw that the other characteristic of a compact manifold without boundary is the sum of the indexes of a vector field at its singular points when the vector field is transverse to the zero section of the tangent bundle. And we want to extend such result for vector fields with isolated singularities. The first step is defining the index for an isolated singularity of a vector field, and then we will see that the formula still holds, the so-called Poincaré Hopf theorem. Then we are going to see some geometrical interpretations of the Euler characteristic for the case of compact orientable surfaces. And finally, we are going to see a very cool result. There exists a vector field defined in a compact manifold without boundary, a vector field without singularities, if and only if the Euler characteristic is zero. There is one implication that is very simple. Indeed, if there exists a vector field with no singularities, it is clear that the Euler characteristic is zero by, for instance, Poincaré Hopf theorem. But we are going to see that the reciprocal holds. If the Euler characteristic is zero, then we can construct a vector field with no singularities. So we want to extend the definition of the index of a vector field to the case of isolated singularities. Let us consider first the case that we already know, a vector field that at a singularity is transverse to the zero section of the tangent bundle. And for that case, we are going to give an alternative definition. Indeed, consider an open ball in Rn and a vector field defined in an open neighborhood of the closure of the ball. And assume the conditions that are going to assume, okay, is that f of x is different than 0 for every x in the closure of the ball minus x0, and the point x0 is going to be an isolated singularity. This condition, the regularity of x0, is just that the vector field is transverse to the zero section. So we consider this map, the map from the boundary of D to the sphere of dimension n-1 that sends y to the image of y by f divided by its norm. And since the image of y for the points in the boundary is different than 0, this is well defined and it's a continuous map. And what the theorem says is that the index of the vector field f at the point x0 is just the degree of g. Okay, we are going to consider that the point x0 is the origin. Okay, that's not, the proof is the same. And so, okay, what we have is that we associated to f a map from the boundary of D to Sn-1. Now we are going to consider a homotopy, and indeed a homotopy of vector fields. Okay, so we are going to define ft of y as just the image of ty divided by t, and that for t in the interval 0, 1 that is open at 0 and closed at 1. Okay, all these vector fields still have an isolated singularity, and the linear part at the origin is always the same. So it is an homotopy of vector fields with just a singularity, and such that all vector fields are transverse to the zero section at 0. Okay? Moreover, we can consider f0 by definition as just the differential of f at 0. And in this way, we get that ft is a homotopy, okay, of vector fields with an isolated singularity such that that isolated singularity is always a regular point. Very good. What happens here is that the index of at the point x0, which is 0, of the vector field f0 is going to be equal to the index at the same point of f1, which is just equal to f. This is in particular because the differential of all these maps at 0 is the same. So they all preserve orientation, or they all reverse orientation. But what we have is that the degree, now to f we associated g, but to every ft we can associate a gt. Okay, built in exactly the same way. Okay, and what we have is that the degree of G0, which is the map that we are associating to F0, which is linear, is going to be the degree of G1. But the degree of G1 is the degree of G. So in order to prove that the index of F at 0 is equal to the degree of G, it suffices to show that the index of f0 at 0 is the degree of g0. So it suffices to consider that f is linear, okay? So we can suppose, by replacing f with f0, that f is linear. And of course, that it's that it's a regular linear map, because that's the condition. The differential at 0 is regular. So, okay, now that we know that it is linear, we can consider another homotopy. Okay, so let ht a homotopy in the linear group, such that, for instance, h0 is equal to f, and h1 is an element in the orthogonal group. Okay, great. So what happens is that the index at 0 of h0, this h0 was equal to f, is going to be equal to the index at 0 of h1. Okay, because we are considering a path of linear maps, okay, that are all isomorphisms, so either all of them are orientation preserving, or all of them are orientation reversing. In any case, these indexes are the same. And what we get is that the degree of the map G associated to F, to H0, is going to be equal to the degree of the map G associated to H1, because these two maps are homotopic and the degree is a homotopy invariant. So it suffices to prove that the quality of the index at 0 of H1 and the degree of the map G associated to H1. Okay, what's that map? The map G associated to H1. We have here the boundary of D and Sn minus 1, right? And it's a map that sends Y into the image by H1 divided by the norm, right? But what happens is that all elements in this boundary have norm equal to R, because that's the ball of center 0 and radius R. So in particular, since an element of the orthogonal group, and H1 belongs by construction to the orthogonal group, preserves distances, we have that the denominator is always equal to r. Yeah? And now we can actually compose here with a map from Sn minus 1 to this boundary, which is the map that sends y to r times y, okay? And that this is just an orientation preserving diffeomorphism. So the degree of this map is going to be the degree of the composition. But the degree of the composition is actually the degree of the map H1, because the composition is equal to H1. Okay, and what we know is that if we have an element of the orthogonal group, okay, the degree of the map that this element of the orthogonal group induces in the sphere is equal to 1 if and only if the determinant of this element of the orthogonal group is equal to 1. So we have that the degree of this map G H1 is equal to 1 if and only if the determinant of H1 is equal to 1. H1 as an element of the orthogonal group. But that determinant is the index of, the index of H1 at 0. So it's if and only if the index of H1 at 0 is equal to 1. So we have that the index of H1 at 0 and the degree of the G associated to H1 are the same. So this completes the proof. So now we can extend the definition of index. Let us consider again a vector field F defined in the neighborhood of the closure of an open ball, okay, and assume that, again, this is not right. What we are going to assume is that f of x is different than 0, than the 0 of Rn, for every x that belongs to the closure of t minus the point x0, and the image of x0 is equal to 0. So we're going to assume is that the unique singularity of f in the closed ball is indeed the point x0. So we can consider this map, and we defined the index of f at the point x0 as just the degree of g. Okay, we already saw that in the transversal case, that is the usual definition of index. And indeed, this is not going to depend of r. If we consider s smaller than r, what we get when we consider here the boundaries of the balls of center x0 and radius s is that when these radius vary, we are obtaining homotopic maps from spheres to Sn minus 1. And as a consequence of that, the degrees of all these maps are the same. So indeed, what we are going to have is that if we consider a smaller ball and the boundary of a smaller ball, the degree is going to be the same. So the definition does not depend on the choice of R. Okay? This is an invariant up to diffeomorphism. One way of seeing this is by using a similar technique as in the proof of this result for the transversal case. What we can do is deforming the diffeomorphisms via anisotropy so that they are linear. And in that case, it's quite simple to prove that the index indeed is going to be the same. It's obvious in the case in which the diffeomorphism preserves orientation, but it is also true when the diffeomorphism is orientation reversing. Let us consider a few examples of vector fields with isolated singularities. In the first case, when we turn once around the origin, so that's the vector field, and as a consequence, the index at this singular point, it's equal to 1, okay? Moreover, a vector field that has this phase portrait is the linear vector field whose matrix is equal to the identity matrix. And obviously the determinant of this matrix is positive, so the index has to be equal to 1. In the second case, a vector field with this phase portrait is the vector field whose matrix is minus the identity. And so the determinant is still positive, so the index is equal to 1. Indeed, the index of a vector field at a singular point and minus the vector field for dimension 2 is the same. Okay, moreover, we can see that when we turn once around the origin in counterclockwise sense, so that's the vector field. Here, in the third case, there is a vector field, again, a linear vector field with that phase portrait, and is the linear vector field with this matrix. The determinant is -1, and so the index is also -1. And in this case, when we turn once around the origin in counterclockwise sense, the vector field turns -1 time. Here, for instance, from the first vector to the second, we have that the second is the result of rotating the first minus pi over 2 degrees. Okay, when we go from here to here, the vector has rotated minus pi radians, sorry. Here, minus 3 pi over 2 radians, and here we get to minus 2 pi radians. So the index is -1. In this case over here, we have again that the vector field rotate once around the origin after making a turn, and so the index is also equal to 1. This vector field over here is going to be 1, okay, because the arrows are essentially, it's like this vector field, but changing the orientation of the arrows. This case, the index is going to be also equal to 1. Indeed, these two vector fields are homomorphic. And in the last case, okay, we're going to have a picture like this one, okay. And what happens is that when we go from here to here, we have rotated by radians. And when we go from here to here, we have rotated 2 pi radians. So after doing half a turn, the vector field has rotated a whole turn. And from here to here, the vector field rotate once again. So the index of this vector field is going to be equal to 2. It's an example of a vector field that has index different than 1 and -1. And it's an example, of course, of an isolated singularity at which the vector field is not transverse to the 0 section of the tangent bundle. Let us see now Poincaré Hopf theorem. Okay, we know that this formula holds if we have a compact differentiable manifold without boundary and a vector field that is transverse to the 0 section of the tangent bundle. And we want to extend this result to the case of a vector field with isolated singularities. What we can do is actually realizing that our vector field C is going to be homotopic to some W, and we can choose W as an approximation of C in the C0 topology. An approximation as good as necessary, okay? And of course, we are going to assume that W is transversal to the zero section of M. What happens here is that our vector field C has a finite number of singularities by hypothesis. And since W is very close to C in the C0 topology, W is going to have singularities close to the singularities of C. Because of the transversality of W with the zero section, W has a finite number of singularities, but all of them are located very close to a singularity of C, okay? Now, what we are going to consider, the previous remark allows us to consider a point y0, which is a singular point of C, and local coordinates, in which we can consider in these local coordinates a closed vault, okay? Here we're going to have the point y0, and there are some singular points of W very close to y0. And we are going to call D to this ball, and we are going to consider some small open balls around these singular points of W such that the closures of these open balls do not intersect and do not intersect with the boundary of D. So this is going to be D1, D2, and so on. Okay, now what we have is that we can define a map capital G from the closure of D minus the union of the DJs. That's going to be a manifold with a boundary to Sn minus 1. And it's the map that sends the point y to W of y divided by its norm. Since the unique singular points of W are these points over here, the singular points that we can call Wj, okay, this is W1, W2, and so on. What happens is that this map is well defined. Okay, in particular, since it's a map defined in the boundary of manifold with boundary that extends to the interior, what happens is that the degree of G restricted to the boundary is going to be 0. Let's call this, for instance, S. Okay, and now, by the properties of the orientation induced in the boundary of a manifold with boundary, what we have is that this is going to be the degree of the restriction of G to the boundary of D minus the sum of the degree of G restricted to the boundary of the DJs. Okay, but we know that by the first result that we proved today, this is going to be the index at the point Wj of the vector field capital W. All right, so we have this sum. And here we have the restriction of G to the boundary of D. So the map that sends the boundary of D to this expression. But since W is very close to C, this map is homotopic to the map that we obtain when we replace here C with W. And that's the definition of the index. And since these two maps are homotopic, that implies that this degree over here is going to be the index of the point y0, at the point y0 of the vector field C. Okay. Okay, and we know that this is going to be equal to 0. So what happens is that we are in a situation in which C has finitely many singular points. Okay, in the neighborhood of these points are all the singular points of the vector field W. Okay, and what happens, let's say y1, sorry, y1, y2, y3, and for instance, what we prove is that the index of C at y1 is going to be the sum of the indexes of the w's close to y1 of w, okay? But we have an analogous result for y2. It's going to be the sum of indexes of w now at this point over here. And the same thing for y3. The index of C at y3 is going to be the sum of the indexes of w at these points. So when we add all these equalities, what we get to the left is just the sum of the indexes of C at its singular points. And what we get to the right is the sum of the indexes of W at its singular points. But that's just the Euler characteristic. So in this way, we complete the proof of Poincaré Hoph's theorem. This is a picture of a compact orientable surface of genus 4. Okay, it has indeed 4 holes. And we can compute the Euler characteristic by considering a vector field and counting the indexes at its singular points. Indeed, we can consider the gradient of a height function. Okay, and in the vector field that is considering the picture, this point is a source, and so as we saw, the index associated to this point is going to be equal to 1, and the bottom point is going to be a sink, an attractor, and so the index is going to be also 1. For every of the holes, we have 2 singular points located here and here. Here, 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 and here. And these points are saddles. Okay, we have one direction in which actually the trajectory, there are trajectories incoming to that point, and here we have trajectories getting out, getting away from the point. Okay, we are going to have at these points a picture that is going to be something like this. Okay, and for saddles, the index is -1. So we have -1, -1, a bunch of -1s. If we sum the indexes at all these singular points, what we get is -6. So the other characteristic of this compact orientable surface is -6, right? But if we consider, for instance, as a compact orientable surface of genus G, by considering an analogous vector field, what we get is that we are going to have a source and a sink whose contribution is going to be 1. The indexes of these points are equal to 1. And for any of the G holes, we have 2 singular points that are saddles. and whose index is -1. So the Euler characteristic in such a case is going to be 2 minus 2 times g, okay, as it is well known. Now let us provide another geometrical interpretation of the Euler characteristic of a compact orientable surface without boundary. So we can consider a triangulation of our surface. Okay, it's a division of our surface in triangles, and we can actually consider a vector field that has the following form. Okay, in every face we consider a source in an interior point, then in every edge we consider here a saddle, okay, and in the vertices we put sinks, and we actually can base the vector fields that are considered in this way to obtain a global vector field. Now we want to calculate the Euler characteristic, and for every face there is an interior singular point. Okay, since such a singular point is the source, its index is equal to 1, so the contribution of the interior points of faces is just the number of faces. Now we want to consider the edges, and indeed the interior points of the edges, these middle points, and their contributions is going to be equal to -1 because these singularities are saddles. So the contribution of the interior points of the edges is going to be minus the number of edges. The remaining singular points are the vertices, but these vertices are indeed sinks, and as a consequence their indexes are equal to 1. So their contribution is going to be equal to the number of vertices. As a consequence, we get a very well-known formula that says that given a triangulation of a compact surface, okay, without manifold, of course, we get that the Euler characteristic is the number of faces minus the number of edges plus the number of vertices of a triangulation. Let us give a necessary and sufficient condition for the existence of a vector field with no singularities. So let M be a compact connected differentiable manifold without boundary. Then there exists a vector field with no singularities on M if and only if the Euler characteristic is equal to 0. And in order to prove the theorem, we are going to use the following lemma. Let F be a infinity map from W to Rn, where W is a connected compact n-manifold with non-empty boundary. Suppose that the preimage of 0 is a finite subset of the interior of W. Then the restriction of F to the boundary of W can be extended to W as a map that has no zeros if and only if the sum of the indexes of F at its zeros is equal to 0. Okay, so we are going to prove in this theorem, what we are going to do is proving the part that is not proved yet, so that the Euler characteristic being equal to 0 implies the existence of a vector field with no singularities, and during the proof we are going to exhibit and prove a simple version of the lemma. Okay, so assume that the Euler characteristic of M is equal to 0. Okay, let C be a C infinity vector field that is transverse to the 0 section. This vector field has a finite set of singularities because of transversality. So what we are going to consider is C infinity diffeomorphism. First of all, we are going to fix one point in M, And there exists a C-infinity diffeomorphism such that the diffeomorphism makes all these points in the singular set of C to be very close to Y0, such that the image of the singular set is contained in an a priori fixed neighborhood of Y0. So up to replace C with its push forward by phi, we can suppose that all singularities of C are very close to Y0. Okay, and that allows us to work in local coordinates. So we are going to consider some local coordinates. Okay, Y0 we can suppose that it's 0. So we are going to work in a neighborhood of a closed ball such that the open ball contains all singularities. So our singularities are here, right? And now let us explain what's our goal. Our goal is the following, is extending the map C, the vector field, which is defined in particular in the boundary of D. D is going to be just the open ball. This is a map that takes value in the complement of 0 because the boundary of D contains no singularities. We want to extend this map to the closure of D, obviously as a map whose target space is still the complement of 0. We want no singularities. If we are able of achieving this, it's game over, because we can define C outside of the ball, of the open ball, as the all C, and in the closed ball, it's going to be just the extension of this map. That's going to provide a continuous vector field with no singularities, and that's what we want. If we deform a little bit, we obtain a C-infinity vector field with no singularities. So we want this. We are going to consider an auxiliary map that we are going to call capital G, and it's going to be just the quotient of the vector field by its norm. Simple as that. And what happens in this situation is that we can extend C. Okay, we have this thing over here. First of all, what we are going to realize is that this map is actually homotopic to the restriction of capital G to the boundary of D. Okay, capital G is defined in every point of the closed ball except the singularities, so in particular in the boundary of D. And the homotopy is very simple because it's just T times C plus 1 minus T times G. When you have a point in which the value of C is not 0, C of Y and G of Y are 2 points in the same half line. And so the convex combination, when T belongs to 0, 1, is not going to vanish. So these two maps are homotopic, right? In particular, extending extending C, extending the restriction of C to the boundary to the closed ball is equivalent to extending the restriction of capital G to the boundary of D. Okay, that we can consider as a map from the boundary of D to Rn minus 0. And this is a consequence of the homotopy extension theorem. Okay, the homotopy extension theorem. But now we can realize that this is equivalent to extending the map capital G when we consider it as a map from the boundary of D to Sn minus 1. And we want to extend it to the closed ball as a map whose target domain is Sn minus 1. Obviously, going from here to here, it's very simple, it's obvious. And the other implication is also simple because if, for instance, H is the extension here, we get an extension here by considering H over its norm. So what we get is that our goal, that is, the goal is here, is equivalent to this order property. But this is a map between two spheres of dimension -1, and we know by the theorem that implied Hopf's theorem that this happens if and only if the degree of the restriction of capital G to the boundary of D is equal to 0. So we have to prove that this degree is 0. If we are able of proving this, it's over. We won. Okay? So we have to show that the degree of the restriction of capital G to the boundary of D is equal to 0. Right. Let's consider the picture again of the closed ball and of the singularities. And we are going to consider some small open balls that we are going to call D1, D2, and so on, such that the closed balls are contained in the closure of D, and these closed balls do not intersect. And they are, of course, neighborhoods of the singularities. What happens is now we can consider a manifold with boundary, which we are going to call S. And it's going to be the closure of D minus the union of the open balls. This is S, okay? Is the big ball minus the small balls. And what happens is that a G is indeed defined as a map from S to Sn minus 1, because capital G is defined in every point that is non-singular, and we are removing a neighborhood of singular points. Okay, now since capital G is here a map from a manifold with boundary of dimension n to a sphere of dimension n minus 1, what we get is that the existence of this extension from the boundary of S to S implies that the degree of capital G restricted to the boundary of S is equal to 0, right? And now, by using the convention that we have for the orientation induced in the boundary of a manifold with boundary, we get that the degree of capital G restricted to the boundary of D is going to be the sum of the degrees of the capital G restricted to the boundary of the DJs. But we know by the definition of index that this is the sum for y in the singular set of C of the index of C at the point y. Okay? In this way, we get the lemma. Okay? We know that in order to extend, we need degree 0, and this is going to happen if and only if the sum of the indexes is 0. And what we want now is using the hypothesis. We know that the sum of these indexes is equal to the Euler characteristic by Poincaré Hopf's theorem. And by hypothesis, the Euler characteristic is 0. So the degree of this map is 0, and that's exactly what we want to prove. So this completes the proof of the theorem. We can interpret Poincaré Hopf theorem as a result that says that the number of singular points of a vector field with isolated singularities is just the Euler characteristic, of course, when we give proper weights to the singular points. We would like to obtain an analog of this result for self-maps and fixed points, so counting the number of fixed points of self-map. For that, we would like to fit this problem, counting the number of fixed points of a self-map, in the setup provided by intersection theory. And we will see in our next lecture that this is possible. Indeed, we are going to see an analog of Poincaré Hopf theorem for the case of self-maps, a formula that counts the number of fixed points, and that result is called Lefschetz fixed point theorem. So it's going to be an interesting lecture in which we are going to be able of counting fixed points of self-maps. And indeed, we are going to relate the two theories, the theory that we saw for vector fields with the theory that we are going to see in the next lecture for self-maps. Thank you for your attention.